Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Machine Learning Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You have trained a deep neural network model on Google Cloud. The model has low loss on the training data, but is performing worse on the validation data. You want the model to be resilient to overfitting. Which strategy should you use when retraining the model? The options are: Option A, apply a dropout parameter of 0.2 and decrease the learning rate by a factor of 10. Option B, apply a L2 regularization parameter of 0.4 and decrease the learning rate by a factor of 10. Option C, run a hyperparameter tuning job on AI platform to optimize for the L2 regularization and dropout parameters. Option D, run a hyperparameter tuning job on AI platform to optimize for the learning rate and increase the number of neurons by a factor of 2.
To arrive at the correct answer, we focus on the keywords: low loss on the training data, performing worse on the validation data, resilient to overfitting.
The correct answer is option C, run a hyperparameter tuning job on AI platform to optimize for the L2 regularization and dropout parameters.
Why is this correct? C. Running a hyperparameter tuning job systematically finds the optimal values for L2 regularization and dropout, which are standard and highly effective techniques to combat overfitting without relying on arbitrary manual values. Why are the others incorrect? A. Manually applying an arbitrary dropout parameter of 0.2 is not a best practice, as it relies on guesswork instead of optimizing the hyperparameter based on the model's actual performance. B. Hardcoding an L2 regularization parameter of 0.4 is suboptimal because the ideal value depends heavily on the specific dataset and model, requiring tuning rather than an arbitrary guess. D. Increasing the number of neurons by a factor of 2 increases model complexity and capacity, which will likely exacerbate overfitting rather than mitigating it.
You are an ML engineer at a global shoe store. You manage the ML models for the company's website. You are asked to build a model that will recommend new products to the user based on their purchase behavior and similarity with other users. What should you do? The options are: Option A, build a classification model. Option B, build a knowledge-based filtering model. Option C, build a collaborative-based filtering model. Option D, build a regression model using the features as predictors.
To arrive at the correct answer, we focus on the keywords: recommend new products, purchase behavior, similarity with other users.
The correct answer is option C, build a collaborative-based filtering model.
Why is this correct? C. Collaborative filtering models recommend items by identifying patterns in historical user interactions and finding similarities between users' purchase behaviors. Why are the others incorrect? A. A classification model predicts categorical labels and is not designed for recommending products based on user-to-user similarity. B. Knowledge-based filtering relies on explicit rules or domain knowledge about users and items, not on historical purchase behavior or user similarities. D. A regression model predicts continuous numerical values, which is inappropriate for generating discrete product recommendations.
Refer to the attached Picture 1, reference exhibit. Your organization's call center has asked you to develop a model that analyzes customer sentiments in each call. The call center receives over 1 million calls daily, and data is stored in cloud storage. The data collected must not leave the region in which the call originated, and no personally identifiable information, PII, can be stored or analyzed. The data science team has a third-party tool for visualization and access which requires a SQL ANSI 2011 compliant interface. You need to select components for data processing and for analytics. How should the data pipeline be designed? The options are: Option A, 1 equals Dataflow, 2 equals BigQuery. Option B, 1 equals pub/sub, 2 equals Datastore. Option C, 1 equals Dataflow, 2 equals Cloud SQL. Option D, 1 equals Cloud Function, 2 equals Cloud SQL.
To arrive at the correct answer, we focus on the keywords: SQL ANSI 2011 compliant interface, data processing, analytics.
The correct answer is option A, 1 equals Dataflow, 2 equals BigQuery.
Why is this correct? A. Dataflow is ideal for scalable data processing, Component 1, and orchestrating API calls. BigQuery, Component 2, provides the required SQL ANSI 2011 compliant interface for large-scale analytics. Why are the others incorrect? B. Pub/sub is a messaging service, not a data processing engine. Datastore is a NoSQL database and does not provide a SQL ANSI 2011 compliant interface. C. While Dataflow is correct for data processing, Cloud SQL is designed for transactional database workloads, OLTP, not the large-scale analytics required. D. Cloud functions are suited for lightweight, event-driven tasks rather than orchestrating complex, large-scale data pipelines. Cloud SQL is not optimal for large-scale analytics.
You have a functioning end-to-end ML pipeline that involves tuning the hyperparameters of your ML model using AI platform, and then using the best-tuned parameters for training. Hypertuning is taking longer than expected and is delaying the downstream processes. You want to speed up the tuning job without significantly compromising its effectiveness. Which actions should you take? Choose 2. The options are: Option A, decrease the number of parallel trials. Option B, decrease the range of floating point values. Option C, set the early stopping parameter to true. Option D, change the search algorithm from Bayesian search to random search. Option E, decrease the maximum number of trials during subsequent training phases.
To arrive at the correct answer, we focus on the keywords: tuning the hyperparameters, taking longer than expected, speed up the tuning job, without significantly compromising its effectiveness.
The correct answers are option C, set the early stopping parameter to true. And option E, decrease the maximum number of trials during subsequent training phases.
Why is this correct? C. Early stopping automatically halts poorly performing trials before they complete, significantly reducing tuning time without missing optimal parameters. E. Decreasing the maximum number of trials directly limits the overall search duration, speeding up the process while still evaluating the most promising regions. Why are the others incorrect? A. Decreasing the number of parallel trials reduces concurrency, which would actually increase the total wall clock time required for the tuning job. B. Decreasing the range might cause you to miss the optimal hyperparameters, compromising effectiveness without necessarily guaranteeing a faster tuning process. D. Random search is generally less efficient than Bayesian optimization and might require more trials to find good parameters, thereby compromising effectiveness.
You work for an online retail company that is creating a visual search engine. You have set up an end-to-end ML pipeline on Google Cloud to classify whether an image contains your company's product. Expecting the release of new products in the near future, you configured a retraining functionality in the pipeline so that new data can be fed into your ML models. You also want to use AI Platform's continuous evaluation service to ensure that the models have high accuracy on your test dataset. What should you do? The options are: Option A, keep the original test dataset unchanged even if newer products are incorporated into retraining. Option B, extend your test dataset with images of the newer products when they are introduced to retraining. Option C, replace your test dataset with images of the newer products when they are introduced to retraining. Option D, update your test dataset with images of the newer products when your evaluation metrics drop below a pre-decided threshold.
To arrive at the correct answer, we focus on the keywords: release of new products, retraining functionality, continuous evaluation service, test dataset.
The correct answer is option B. Extend your test dataset with images of the newer products when they are introduced to retraining.
Why is this correct? B. To accurately evaluate the retrained model on both existing and newly introduced products, the test dataset must be extended to include the new products while retaining the old ones. Why are the others incorrect? A. Keeping the test dataset unchanged prevents the continuous evaluation service from measuring the model's accuracy on the newly introduced products. C. Replacing the test dataset entirely would mean the model is no longer evaluated on older products, risking undetected performance regressions on them. D. Waiting for evaluation metrics to drop before updating the test dataset is reactive. The test set should immediately reflect the new product distribution.
You are developing an ML model in a Vertex AI Workbench notebook. You want to track artifacts and compare models during experimentation using different approaches. You need to rapidly and easily transition successful experiments to production as you iterate on your model implementation. What should you do? The options are: Option A, 1. Initialize the Vertex SDK with the name of your experiment. Log parameters and metrics for each experiment, and attach dataset and model artifacts as inputs and outputs to each execution point. 2. After a successful experiment, create a Vertex AI pipeline. Option B, 1. Initialize the Vertex SDK with the name of your experiment. Log parameters and metrics for each experiment, save your dataset to a cloud storage bucket, and upload the models to Vertex AI Model Registry. Point 2. After a successful experiment, create a Vertex AI pipeline. Option C, 1. Create a Vertex AI pipeline with parameters you want to track as arguments to your pipeline job. Use the metrics, model, and dataset artifact types from the Kubeflow pipeline's DSL as the inputs and outputs of the components in your pipeline. Point 2. Associate the pipeline with your experiment when you submit the job. And the remaining options are: Option D, 1. Create a Vertex AI pipeline. Use the dataset and model artifact types from the Kubeflow pipeline's DSL as the inputs and outputs of the components in your pipeline. Point 2. In your training component, use the Vertex AI SDK to create an experiment run. Configure the log_params and log_metrics functions to track parameters and metrics of your experiment.
To arrive at the correct answer, we focus on the keywords: Vertex AI Workbench Notebook, track artifacts, and compare models during experimentation, rapidly and easily transition successful experiments to production.
The correct answer is option A, 1. Initialize the Vertex SDK with the name of your experiment. Log parameters and metrics for each experiment, and attach dataset and model artifacts as inputs and outputs to each execution. Point 2. After a successful experiment, create a Vertex AI pipeline. Review the options on screen.
Why is this correct? A. Initializing the Vertex SDK and logging directly in the notebook enables rapid experimentation. Attaching artifacts as inputs/outputs maintains lineage for comparison. Creating a pipeline afterward provides an easy transition to production. Why are the others incorrect? B. Saving datasets to a bucket and uploading models to the model registry manually fails to automatically track their lineage within the experiment run, hindering effective artifact tracking and model comparison. C. Building a Kubeflow pipeline for early experimentation introduces unnecessary overhead, violating the need to rapidly iterate on the model implementation within the notebook environment. D. Creating a Vertex AI pipeline upfront for experimentation slows down iteration. While logging within a component works for pipelines, it adds complexity that contradicts the rapid notebook-based experimentation requirement.
You have been asked to develop an input pipeline for an ML training model that processes images from disparate sources at a low latency. You discover that your input data does not fit in memory. How should you create a dataset following Google recommended best practices? The options are: Option A, create a tf.data, dataset.prefetch transformation. Option B, convert the images to TF tensor objects, and then run dataset.from_tensor_slices. Option C, convert the images to TF tensor objects, and then run tf.data, dataset.from_tensors. Option D, convert the images into TF records, store the images in cloud storage, and then use the tf.data API to read the images for training.
To arrive at the correct answer, we focus on the keywords: input pipeline, images from disparate sources, low latency, input data does not fit in memory, Google recommended best practices.
The correct answer is option D, convert the images into TF records, store the images in cloud storage, and then use the tf.data API to read the images for training.
Why is this correct? D. TF records are the Google recommended format for reading data efficiently from cloud storage. The tf.data API is the standard for building performant input pipelines when the dataset is too large to fit in memory. Why are the others incorrect? A. The prefetch transformation improves pipeline performance by overlapping data preprocessing and model execution, but it does not address how to load data that exceeds memory capacity. B. Dataset.from_tensor_slices is intended for small datasets that can fit entirely in memory, which directly contradicts the problem statement's constraints. C. TF.data dataset.from_tensors loads and combines all inputs into a single tensor in memory. This is unsuitable for datasets that do not fit in memory.
You developed a Vertex AI ML pipeline that consists of pre-processing and training steps, and each set of steps runs on a separate custom Docker image. Your organization uses GitHub and GitHub Actions as CI/CD to run unit and integration tests. You need to automate the model retraining workflow so that it can be initiated both manually and when a new version of the code is merged in the main branch. You want to minimize the steps required to build the workflow while also allowing for maximum flexibility. How should you configure the CI/CD workflow? The options are: Option A, trigger a cloud build workflow to run tests, build custom Docker images, push the images to artifact registry, and launch the pipeline in Vertex AI pipelines. Option B, trigger GitHub Actions to run the tests, launch a job on Cloud Run to build custom Docker images, push the images to artifact registry, and launch the pipeline in Vertex AI pipelines. Option C, trigger GitHub Actions to run the tests, build custom Docker images, push the images to artifact registry, and launch the pipeline in Vertex AI pipelines. Option D, trigger GitHub Actions to run the tests, launch a cloud build workflow to build custom Docker images, push the images to artifact registry, and launch the pipeline in Vertex AI pipelines.
To arrive at the correct answer, we focus on the keywords: GitHub and GitHub Actions as CI/CD to run unit and integration tests, minimize the steps required, maximum flexibility.
The correct answer is option D, trigger GitHub Actions to run the tests, launch a cloud build workflow to build custom Docker images, push the images to artifact registry, and launch the pipeline in Vertex AI pipelines.
Why is this correct? D. Using existing GitHub Actions for testing minimizes setup steps, while triggering Cloud Build leverages native GCP integration for building images and launching Vertex AI pipelines, providing maximum flexibility and security. Why are the others incorrect? A. Moving the existing tests to Cloud Build ignores the organization's current GitHub Actions CI/CD setup, increasing the steps required to build the workflow. B. Cloud Run is a managed compute platform for deploying and serving containerized applications, not a service designed to build Docker images. C. Building images and launching pipelines directly within GitHub Actions requires complex GCP credential management and consumes GitHub runner resources, reducing flexibility and security compared to Cloud Build.
Your organization's employee onboarding team wants you to build an interactive self-help tool for new employees. The tool needs to receive queries from users and provide answers from the organization's internal documentation. This documentation is spread across standalone documents such as PDF files. You want to build a solution quickly while minimizing maintenance overhead. What should you do? The options are: Option A, create a custom chatbot user interface hosted on App Engine. Use Vertex AI to fine-tune a Gemini model on the organization's internal documentation. Send users queries to the fine-tuned model by using the custom chatbot and return the model's responses to the users. Option B, deploy an internal website to a Google Kubernetes Engine (GKE) cluster. Build a search index by ingesting all of the organization's internal documentation. Use Vertex AI vector search to implement a semantic search that retrieves results from the search index based on the query entered into the search box. Option C, use Vertex AI Agent Builder to create an agent. Securely index the organization's internal documentation to the agent's data store. Send users queries to the agent and return the agent's grounded responses to the users. And the remaining options are: Option D, deploy an internal website to a Google Kubernetes Engine (GKE) cluster. Organize the relevant internal documentation into sections. Collect user feedback on website content and store it in BigQuery. Request that the onboarding team regularly update the links based on user feedback.
To arrive at the correct answer, we focus on the keywords: interactive self-help tool, receive queries from users and provide answers, internal documentation, standalone documents such as PDF files, build a solution quickly while minimizing maintenance overhead.
The correct answer is option C, use Vertex AI Agent Builder to create an agent. Securely index the organization's internal documentation to the agent's data store. Send users queries to the agent and return the agent's grounded responses to the users. View the options on screen.
Why is this correct? C. Vertex AI Agent Builder provides a quick, low-maintenance way to create conversational agents that use Retrieval-Augmented Generation (RAG) to ground answers directly in unstructured enterprise data like PDFs. Why are the others incorrect? A. Fine-tuning a model on documents is inefficient for factual retrieval and has high maintenance overhead compared to RAG. Building a custom App Engine UI also increases development time. B. Managing a GKE cluster and building a custom semantic search solution requires significant development effort and introduces high maintenance overhead compared to a fully managed agent solution. D. Deploying on GKE and relying on manual document organization and link updates introduces excessive maintenance overhead and fails to provide an automated, query-based self-help tool.
You work for an international manufacturing organization that ships scientific products all over the world. Instruction manuals for these products need to be translated to 15 different languages. Your organization's leadership team wants to start using machine learning to reduce the cost of manual human translations and increase translation speed. You need to implement a scalable solution that maximizes accuracy and minimizes operational overhead. You also want to include a process to evaluate and fix incorrect translations. What should you do? The options are: Option A, create a workflow using Cloud Function triggers. Configure a Cloud Function that is triggered when documents are uploaded to an input cloud storage bucket. Configure another Cloud Function that translates the documents using the Cloud Translation API and saves the translations to an output cloud storage bucket. Use human reviewers to evaluate the incorrect translations. Option B, create a Vertex AI pipeline that processes the documents, launches an AutoML translation training job, evaluates the translations and deploys the model to a Vertex AI endpoint with auto-scaling and model monitoring. When there is a predetermined skew between training and live data, retrigger the pipeline with the latest data. Option C, use AutoML translation to train a model. Configure a translation hub project and use the trained model to translate the documents. Use human reviewers to evaluate the incorrect translations. And the remaining options are: Option D, use Vertex AI custom training jobs to fine-tune a state-of-the-art open-source pre-trained model with your data. Deploy the model to a Vertex AI endpoint with auto-scaling and model monitoring. When there is a predetermined skew between the training and live data, configure a trigger to run another training job with the latest data.
To arrive at the correct answer, we focus on the keywords, translated to 15 different languages, scalable solution that maximizes accuracy and minimizes operational overhead, process to evaluate and fix incorrect translations.
The correct answer is option C, use AutoML translation to train a model. Configure a translation hub project, and use the trained model to translate the documents. Use human reviewers to evaluate the incorrect translations. Review the options on screen.
Why is this correct? C. AutoML translation trains high-accuracy custom models. Translation Hub provides a managed, scalable document translation workflow that minimizes operational overhead and natively supports human review to evaluate and fix incorrect translations. Why are the others incorrect? A. Cloud Translation API provides generic translations, which may not maximize accuracy for scientific products. Building and maintaining a custom cloud function workflow increases operational overhead compared to managed solutions. B. While AutoML translation improves accuracy, this approach lacks the required process to evaluate and fix incorrect translations. Building custom Vertex AI pipelines adds unnecessary operational overhead for document translation. D. Fine-tuning a custom model on Vertex AI significantly increases operational overhead. Additionally, this solution fails to provide the required process for human reviewers to evaluate and fix incorrect translations.
You are training an LSTM-based model on AI platform to summarize text using the following job submission script. Cloud AI platform job submit training $job_name /package path $trainer _package _path /module name $main _trainer _module /job dr. $job_dir /region $region /scale tier basic /epochs 20 /batch_size equals 32 /learning rate equals 0.001 you want to ensure that training time is minimized without significantly compromising the accuracy of your model. What should you do? The options are: Option A, modify the epochs parameter. Option B, modify the scale tier parameter. Option C, modify the batch size parameter. Option D, modify the learning rate parameter.
To arrive at the correct answer, we focus on the keywords, scale tier basic, training time is minimized, without significantly compromising the accuracy.
The correct answer is option B, modify the scale tier parameter.
Why is this correct? B. Changing scale tier to a more powerful cluster, like standard_GPU or custom, provides hardware acceleration, GPUs/TPUs. This significantly speeds up the training of computationally intensive LSTM models, reducing time without fundamentally altering the convergence behavior or accuracy. Why are the others incorrect? A. Reducing epochs decreases training time but often causes underfitting, which significantly compromises model accuracy. C. Changing batch size affects gradient estimates and convergence dynamics, which can degrade the model's final accuracy and generalization. D. Increasing the learning rate might speed up initial convergence but risks instability and overshooting the minimum, compromising accuracy.
You have written unit tests for a Kubeflow pipeline that require custom libraries. You want to automate the execution of unit tests with each new push to your development branch in cloud source repositories. What should you do? The options are: Option A, write a script that sequentially performs the push to your development branch and executes the unit tests on Cloud Run. Option B, using Cloud Build, set an automated trigger to execute the unit tests when changes are pushed to your development branch. Option C, set up a cloud logging sync to a pub/subtopic that captures interactions with cloud source repositories. Configure a pub/sub trigger for Cloud Run, and execute the unit tests on Cloud Run. Option D. Set up a cloud logging sync to a pub/subtopic that captures interactions with cloud source repositories. Execute the unit tests using a cloud function that is triggered when messages are sent to the pub/subtopic.
To arrive at the correct answer, we focus on the keywords, automate the execution of unit tests, each new push, cloud source repositories.
The correct answer is option B. Using Cloud Build, set an automated trigger to execute the unit tests when changes are pushed to your development branch.
Why is this correct? B. Cloud Build natively integrates with cloud source repositories to trigger automated builds or tests upon pushes to specific branches. It provides custom environments where required custom libraries can be easily installed. Why are the others incorrect? A manual script requires manual intervention or a separate scheduling system to run, failing to provide the seamless, managed CI/CD automation that Cloud Build offers natively. C. This architecture is unnecessarily complex and indirect. Cloud Build is specifically designed for the CI/CD use case, making a custom logging-based trigger an anti-pattern. D. Triggering a cloud function via cloud logging and pub/sub is an over-engineered workaround. Cloud Build provides a managed CI/CD pipeline natively tailored for running tests upon code pushes.
You work for a gaming company that develops massively multiplayer online (MMO) games. You built a TensorFlow model that predicts whether players will make in-app purchases of more than $10 in the next 2 weeks. The model's predictions will be used to adapt each user's game experience. User data is stored in BigQuery. How should you serve your model while optimizing cost, user experience, and ease of management? The options are: Option A. Import the model into BigQuery ML, make predictions using batch reading data from BigQuery, and push the data to Cloud SQL. Option B. Deploy the model to Vertex AI prediction. Make predictions using batch reading data from Cloud Bigtable, and push the data to Cloud SQL. Option C. Embed the model in the mobile application. Make predictions after every in-app purchase event is published in pub/sub, and push the data to Cloud SQL. Option D. Embed the model in the streaming Dataflow pipeline. Make predictions after every in-app purchase event is published in pub/sub, and push the data to Cloud SQL.
To arrive at the correct answer, we focus on the keywords. Next 2 weeks, user data is stored in BigQuery, optimizing cost, user experience, and ease of management.
The correct answer is option A. Import the model into BigQuery ML, make predictions using batch reading data from BigQuery, and push the data to Cloud SQL.
Why is this correct? A. Importing the model into BigQuery ML allows low-cost, easy-to-manage batch predictions directly on the data. Pushing results to Cloud SQL enables low-latency retrieval for the game server, ensuring a good user experience. Why are the others incorrect? B. Data is already in BigQuery, so moving it to Bigtable and using Vertex AI for batch predictions adds unnecessary cost and management complexity compared to BigQuery ML. C. Embedding the model in the mobile app complicates updates and uses device resources. A 2-week prediction window doesn't require real-time on-device inference. Batch predictions are sufficient and easier to manage. D. A streaming Dataflow pipeline introduces unnecessary cost and management overhead for a 2-week prediction window, which is better suited for simpler, more cost-effective batch processing.
During batch training of a neural network, you notice that there is an oscillation in the loss. How should you adjust your model to ensure that it converges? The options are: Option A. Decrease the size of the training batch. Option B. Decrease the learning rate hyperparameter. Option C. Increase the learning rate hyperparameter. Option D. Increase the size of the training batch.
To arrive at the correct answer, we focus on the keywords, batch training, oscillation and the loss. Adjust your model to ensure that it converges.
The correct answer is option B. Decrease the learning rate hyperparameter.
Why is this correct? B. Decreasing the learning rate reduces the step size in gradient descent, which prevents overshooting the minimum, dampens loss oscillations, and allows the model to converge smoothly. Why are the others incorrect? A. Decreasing the training batch size increases the variance of the gradient estimates, introducing more noise. This would likely exacerbate the oscillations and make convergence more erratic. C. Increasing the learning rate results in larger step sizes during gradient descent. This would exacerbate the overshooting of the minimum, worsening the oscillations and potentially causing the loss to diverge. D. Increasing the batch size reduces gradient noise, but it does not address the primary cause of oscillation, which is a step size that is too large. Decreasing the learning rate is the required adjustment.
You recently developed a deep learning model using Keras, and now you are experimenting with different training strategies. First, you trained the model using a single GPU, but the training process was too slow. Next, you distributed the training across 4 GPUs using tf.distribute.mirrored strategy, with no other changes, but you did not observe a decrease in training time. What should you do? The options are: Option A, distribute the dataset with tf.distribute, strategy.experimental_distribute_dataset. Option B, create a custom training loop. Option C, use a TPU with tf.distribute.tpu strategy. Option D, increase the batch size.
To arrive at the correct answer, we focus on the keywords: distributed the training across 4 GPUs, tf.distribute.mirrored strategy, with no other changes, did not observe a decrease in training time.
The correct answer is option D, increase the batch size.
Why is this correct? D. Distributing training without changing the batch size reduces the per GPU batch size. This underutilizes each GPU and increases communication overhead relative to compute, negating the speedup. Increasing the global batch size restores per-device utilization and improves training speed. Why are the others incorrect? A. Mirrored strategy automatically distributes the dataset across replicas when using Keras model.fit, so explicitly distributing it is unnecessary and won't fix the performance bottleneck. B. A custom training loop provides flexibility but does not inherently solve the issue of GPU underutilization caused by an inadequate batch size. C. Switching to TPUs does not address the root cause of hardware underutilization due to a small per-device batch size, so it may not improve training time.